Transport Layer Security, most commonly called TLS, is one of the most important protocols on the internet. TLS ensures a secure connection between a client, for example a browser, and a server, for example a web service, which owns a cryptographic certificate that proves the server's identity. To establish a secure connection, the client sends a "Hello Client" message and its share of the session key. The server then generates a digital signature over the transcript of this client and the server. Afterwards, it sends the following data to the client: a hello server message, its key share, the generated transcript signature, and the server certificate. Now the server and client have all the information to start communicating securely under a shared key. In practice, however, many clients communicate with one or more servers of a web service. Without any smart distribution of the requests, it might happen that some servers are overloaded while others do not receive any requests. Special proxies acting as load balancers are often used to distribute the amount of requests equally. These load balancers are often used as TLS termination proxies. That means they decrypt every incoming request and sign and decrypt every outgoing request to offload the backend servers from the cryptographic operations. Encryption and decryption operations are often fast. Signature generation, however, sometimes is very costly depending on the signature scheme used. Since the response to every request needs to be signed, the load balancer might become the computational bottleneck themselves. One way to avoid this is to use batch signing. That means instead of signing the transcript of every request individually, groups or batches of transcripts are signed altogether. This is effectively done by putting these transcripts into a Merkle tree. The transcripts of each request are used to build a tree in which two children nodes are hashed to build the parent node. At the end, only the root node is signed. To verify the root signature, the verifier needs to reconstruct the tree. Each user is sent the root signature and their own unique path to the root, which is enough to reconstruct the entire tree. For example, the path for request 1 includes the leaf of request 2, the hash of request 3 and request 4, and the other children of the root node. Similarly, the paths are constructed for the other requests. In our example, this means that, at the cost of a slightly larger response, we only need to generate 1 instead of 6 digital signatures. In terms of TLS, this approach would amortize the most costly computation, which is greatly exasperated with post-quantum signatures. Our team has experimentally evaluated the benefit of this approach for different applications. The results can be found in the ICR ePrint 2023/492. We also have information in our Batch Me If You Can blog post and paper linked in the information. Thank you.